Look up tonight, and every star you can see is, statistically speaking, the exception. Astronomers now have real, direct evidence for a very different kind of world entirely. Planets with no star at all, drifting through the galaxy in permanent dark, warmed only by whatever heat they can generate themselves. One was found this past January, its mass and its distance measured for the first time in history, from a flicker of light that lasted barely 2 days. Others may not even be orphans in the usual sense. Some may never have belonged to a star to begin with. Tonight, we follow these unlit worlds from their first faint statistical trace to the strange, specific physics that might, against every expectation, keep a surprising number of them quietly warm. If you'd like more nights like this one, liking the video and subscribing genuinely helps a small channel like this keep going, and it costs you nothing but a tap. Get comfortable and let your eyes soften. In 3, 2, 1, liftoff. On the 3rd of May, 2024, in the direction of the crowded, star-choked heart of the galaxy, a scattering of telescopes on the ground and one spacecraft far out in the dark were doing what they did most nights, watching. Patiently, methodically, without much expectation of anything unusual, they recorded the steady brightness of star after star after star, the way they had every clear night for years, feeding the numbers back to automated alert systems built to catch the first faint hint of a change. Then, in one small patch of sky among millions, a star that had shone at a perfectly ordinary brightness for as long as anyone had been watching, it grew very slightly brighter, held that brightness for a little under 2 days, and then eased back down to exactly what it had been before. No explosion, no collision, no flare, just a soft, symmetrical climb and fall, the kind of event that, on any other night, in any other survey, might have been filed away and forgotten among 1,000 others just like it. This one was not forgotten, because buried inside that quiet flicker, unseen and unannounced, was the fingerprint of a planet with no sun of its own, moving alone through the dark between the stars, and the astronomers who eventually decoded that fingerprint would go on to do something that had never quite been done before. The man who led that effort has spent the better part of his career listening for exactly this kind of whisper. Subo Dong is a professor at the Kavli Institute for Astronomy and Astrophysics at Peking University, where he has worked since 2013 after earning his doctorate at Ohio State University in 2009. His research has always circled back to the same quiet detective work, tracing faint, fleeting signals back to the massive objects that caused them, whether that meant reconstructing how a star exploded from the afterglow it left behind, or watching the dense star fields toward the middle of our galaxy for the kind of brief gravitational flicker that can betray a planet, or even a black hole, giving off no light of its own. It is not the sort of work that rewards impatience. Most nights bring nothing at all, but on the rare night that something does show up, the payoff can rewrite what an entire field thought it knew, and the flicker recorded on that night in May would turn out to be exactly that kind of night, even if nobody understood its full significance until much later, when the analysis was finally finished and the result was published in the journal Science in the opening days of 2026. To understand why one small brightening event, one small paper, could matter so much, it helps to sit for a moment with an idea that still unsettles a good many astronomers, once they let themselves think about it carefully, that the planets we can actually see and study, the ones tucked into orbit around a star the way a porch light sits fixed beside a front door, may not be the typical case at all. They may simply be the easy case, the case our instruments happen to be built to notice. Astronomers have increasingly come to suspect that a second, far larger population of planets exists alongside the familiar one, worlds that belong to no star whatsoever, that circle nothing, that drift through the space between the stars on paths of their own, lit by nothing but the same faint, distant starlight that reaches every corner of the galaxy in more or less equal and vanishingly small measure. Astronomers call them free-floating planets. Elsewhere you will hear them called rogue planets, orphan planets, nomad planets, even interstellar planets, 4 different names circling the very same idea. And the honest answer to how many of them exist is one of the more interesting stories in modern astronomy, not because the number is settled, but because it keeps changing, and because the way it keeps changing tells you something true about how real science actually works. Picture, for a moment, a small town on a winter evening, every house along the main street with its porch light burning against the dark, familiar and warm and easy to count from a distance. A planet bound to a star is a little like one of those houses. You can find it because its star's light gives its presence away, brightening and dimming in small, telling patterns as the planet crosses in front of it, or tugging the star itself in a slow, betraying wobble. A rogue planet has no porch light to switch on. It generates no glow of its own worth speaking of, and it reflects no borrowed sunlight, because there is no sun nearby to lend it any. If such a world drifted through your own backyard, you would never see it coming. It would be there, solid and real, made of rock or ice or compressed gas, and it would remain completely invisible right up until the moment it was already past. So how, then, does anyone find such a thing at all? The answer traces back to an idea Albert Einstein worked out earlier in the last century as part of his theory of how gravity bends the fabric of space itself. Light, Einstein showed, does not travel in a perfectly straight line past a massive object. It curves slightly, pulled off course by that object's gravity, the way a marble rolling across a stretched sheet of rubber will curve around a heavy weight resting somewhere on that sheet. Einstein himself doubted anyone would ever measure so small an effect, but in 1919, the astronomer Arthur Eddington sailed to a small island off the coast of West Africa to photograph a total solar eclipse, and in the brief darkness of totality, he measured the positions of stars whose light passed close by the eclipsed sun, and found them shifted by just the tiny amount Einstein had predicted. The discovery made front-page news around the world and made Einstein, almost overnight, a household name. What began as a proof about starlight bending around our own sun would, a century later, become the very tool astronomers use to find worlds with no sun at all. If a massive object happens to drift almost exactly between Earth and a much more distant star, that same bending can act very much like a lens, gathering and focusing the distant star's light, making that star appear, briefly, noticeably brighter than it should. As the foreground object continues on its way and the alignment breaks, the brightness eases back down and the whole event is over, usually within days, sometimes within hours. Astronomers call this gravitational microlensing, and it is, at present, the only method that can reveal a planet producing no light of its own, because it does not depend on seeing the planet at all. It depends only on catching the shadow its gravity casts across the light of a star far behind it. It is not, in fairness, the only way a rogue planet has ever been found, only the only way to find the older, smaller, colder ones. A young, free-floating world, still glowing faintly from the leftover heat of its own formation, can occasionally be photographed directly, the way an ordinary star or a distant galaxy is photographed, provided it is massive enough and young enough to still be warm. In the early 2010s, astronomers using ground-based telescopes in Chile and France picked out exactly such an object, drifting only about 100 light-years from Earth, a gas giant several times the mass of Jupiter, faintly glowing, unattached to any star, among the nearest such worlds ever found. Direct images like that one are rare gifts, because they only work for the youngest, warmest, heaviest, free-floating worlds, the ones still bright enough to see. For the vast, cold majority, the ones that formed billions of years ago and have long since finished cooling, gravitational microlensing remains the only window in. There is a catch, though, and it is a significant one, because a microlensing event depends on a chance alignment between three objects drifting independently through space: Earth, the foreground lensing object, and the distant background star. That particular alignment will never happen again. Once it has passed, it is gone, permanently and completely. There is no going back for a second look, no sending a follow-up telescope to confirm what was seen, the way astronomers routinely do with a newly spotted comet or a freshly discovered asteroid. Whatever a survey manages to record during those brief days of brightening is, in a very real sense, all that will ever exist to study. That single constraint has shaped this entire field of research from the very beginning, and it is part of why progress on rogue planets has moved in such an unusual way, not steadily, the way a slow, patient survey might catalogue a new class of star, but in occasional, striking leaps, followed by long stretches of careful, unglamorous revision. For nearly 3 decades now, 2 major survey collaborations have taken on the patient work of watching the galaxy's crowded core for exactly these events. 1. Run from Las Campanas Observatory high in the mountains of Chile, goes by the name of the Optical Gravitational Lensing Experiment. The other, operating out of Mount John University Observatory in New Zealand, is called the Microlensing Observations in Astrophysics Survey. Neither uses the kind of enormous mirror built for deep, dramatic images of distant galaxies. Their telescopes are modest, almost unglamorous by comparison, but they are built for exactly the opposite task, not staring long and hard at one small patch of sky, but sweeping across tens of millions of stars. Night after night, clear sky after clear sky, recording brightness over and over, waiting for the rare handful that will flicker in just the right way. It is, by any honest description, a slow and thankless kind of astronomy. A newer network, built and operated out of South Korea and called the Korea Microlensing Telescope Network, joined the watch more recently still, adding a trio of its own telescopes, spread across 3 separate continents so that the galaxy's core could be tracked around the clock as the Earth turned beneath it. Between the 3 of them, over the decades, these collaborations have quietly become responsible for a large share of every planet ever found through gravitational microlensing, ordinary, star-bound worlds included, long before any turned its attention to the stranger question of what might be flickering past with no star attached at all. It was, fittingly, 2 of these 3 networks working in concert that first caught the flicker Subo Dong's team would eventually trace to a planet with no sun. And it was exactly this kind of patient, repetitive watching that first produced a genuinely startling result. In 2011, a team working with the Microlensing Observations in Astrophysics Survey, led by the astronomer Takahiro Sumi, published an analysis in the journal Nature covering 2 years of accumulated data, and the numbers hidden inside it were difficult to explain any other way than one particular, unsettling conclusion. The team found more short, sharp, brightening events the kind produced by a solitary, Jupiter-sized object, a single world carrying more than 300 times the mass of Earth, rather than a planet still tied to its star, than their models could account for, if such free-floating giants were rare. When they worked the statistics through, the implied population was strikingly large, something close to twice as many free-floating, Jupiter-sized planets as there are stars in the entire galaxy. The claim landed awkwardly from the very start. Theorists who studied how planets actually form struggled to explain how nature could produce giant worlds cast loose in such enormous numbers, and separate surveys searching young star clusters directly, hunting for faint, newly formed planetary mass objects with infrared cameras rather than gravitational flickers, were not turning up nearly enough of them to match. Still, if the number held up, it meant the galaxy's true census of large planets was being dramatically undercounted by every survey that had only ever looked for worlds still bound to a star, and it meant a person could reasonably say that unattached, starless worlds might outnumber the more familiar, orbiting kind by a wide margin. The finding traveled quickly through the scientific community and then out into popular science writing, where a single vivid number, twice as many rogue planets as stars, has a way of sticking long after the careful qualifications and the theorists' unease are forgotten. 6 years later, a much larger, much more careful study set out to test that number directly, and it did not survive the test in the form it had first arrived in. A team working with the optical gravitational lensing experiment, led by the astronomer Primož Mruz, examined more than 2,600 microlensing events, gathered across roughly 50 million stars over 6 full years of observation, something close to 5 times the data behind the original 2011 result, and published their own findings, also in the journal Nature, searching specifically for the same excess of short, sharp brightenings that had suggested such an enormous population of free-floating, Jupiter-sized worlds. They did not find it, at least not at anywhere close to the scale first proposed. Their data placed a firm ceiling on how common such giant rogue planets could possibly be, one at most for roughly every 4 stars in the galaxy, not 2 for every single one. It was, in the plainest terms, a significant correction, an order of magnitude smaller than the number that had captured so much attention 6 years earlier, and it is worth sitting with for a moment, because it says something honest about how this kind of science actually proceeds. A single early result, however striking, however widely repeated afterward, is a beginning rather than a verdict. The number the public remembers is very often not the number that survives. There was, however, a second, quieter thread buried inside that same 2017 analysis, one that would prove, in time, to matter just as much as the correction itself. Among the thousands of events the team examined, a handful lasted for a strikingly short window, mere hours rather than days, far too brief to have been produced by anything as large as Jupiter. The team could not confirm exactly what had caused them. The events were too faint, too fleeting to pin down with real confidence. But their existence hinted at something the original 2011 study had been too coarse an instrument to catch: a population of much smaller free-floating worlds, closer to the size of Earth, or perhaps a modest step above it, that might be common enough to rival or even exceed the number of stars in the galaxy after all, just not in the form anyone had first proposed. The giants, it seemed, had been overcounted. The smaller worlds, quite possibly, had been sitting there all along, simply too faint and too brief for the instruments of the day to properly resolve. Both of these threads, the correction and the hint that followed it, were still sitting exactly where they had been left when Subo Dong's team recorded that quiet flicker on the 3rd of May, 2024. What made Dong's event different from the roughly dozen rogue planet candidates already logged in the years before? It was not that it had been seen. Solitary, starless flickers of this kind had been caught before, now and again, ever since the very first hints of the phenomenon turned up at the start of this century. What made this one different was what the team was able to do with it afterward. In nearly every previous case, all a survey could ever measure was the shape of the brightening curve itself, how quickly it rose, how long it lingered, how quickly it fell, and that shape alone was never quite enough. A small, nearby object and a somewhat larger, more distant one can trace out almost exactly the same curve when viewed from a single vantage point, in the same way that a nearby candle and a much larger, more distant street lamp can appear equally bright to an eye standing in one fixed spot, with no simple way to tell, from brightness alone, which one is truly larger and which is truly closer. For every previous, free-floating planet candidate, mass and distance were tangled together in exactly that way, inseparable, each one only ever estimated statistically, never pinned down on its own. There is a simple way to feel this same problem for yourself, one that has nothing to do with telescopes at all. Hold a finger up in front of your face, close one eye, and notice where it lines up against the wall or the window behind it. Now switch eyes. Keeping the finger still, it appears to jump, shifting slightly against that same background, simply because your two eyes are looking from two very slightly different positions. That small shift is called parallax, and the closer your finger is to your face, the more dramatically it jumps between eyes. Held at arm's length, the shift is smaller still. Astronomers have leaned on this same simple trick for centuries to measure the distance to nearby stars, watching how their position seems to drift against more distant background stars as the Earth itself moves from one side of the Sun to the other over the course of a year. Dong's team applied exactly the same idea, only using two eyes very much farther apart than any two eyes have ever been used before. Dong's team broke the mass and distance tangle by watching the same brief event from two very different places at once. On Earth, ground-based survey telescopes recorded the brightening as it happened. At the same time, roughly 1 million miles farther out in space, the European Space Agency's Gaia spacecraft, an observatory built to chart the positions, distances, and motions of well over 1 billion stars, assembling the single most detailed three-dimensional map of our galaxy ever made, was watching the very same patch of sky from its own separate vantage point, its own eye, so to speak, set impossibly far from Earth's. Because the two vantage points were separated by such a distance, the brightening event did not look quite identical from each. It peaked at a very slightly different moment, and by a very slightly different amount, when viewed from Gaia than when viewed from the ground. That small mismatch, the very same kind of shift your own two eyes produce with an outstretched finger, turned out to be exactly the missing piece of information the tangle required. With two independent perspectives on the very same event instead of one, the team could finally solve for mass and distance separately, rather than settling for one blurred estimate standing in for both. There is a quiet, almost poignant detail worth sitting with here. By the time this analysis was finished and made public, the Gaia spacecraft itself was no longer operating. Its long working life had come to a close in the early days of 2025, not long after it had captured the very starlight this discovery would eventually depend on. In a sense, one of the last meaningful contributions of an instrument built to map the true shape and scale of our galaxy turned out to be helping confirm, for the first time with real confidence, that a planet with no star of its own was exactly where the numbers said it was. After all of that cross-checking, the figures the team arrived at were as follows. The object responsible for the flicker sits at a distance of roughly 9,800 light-years from Earth, out toward the crowded, glittering hub of the Milky Way, and it carries a mass equal to about 22% of Jupiter's own, close enough to the mass of Saturn that many descriptions of it simply call it Saturn-sized. For the first time in the history of this particular hunt, a rogue planet's mass and its distance from Earth had both been measured directly from real, independently cross-checked observation, rather than modeled from theory or estimated from a single, incomplete brightening curve. Roughly a dozen other rogue planet candidates had been proposed in the years before it. This was the first to be pinned down with a confirmed, directly measured weight. Try, for a moment, to picture that particular world as it actually sits tonight, 9,800 light-years off, toward the crowded middle of the galaxy. No sunrise ever touches it, because it has no sun to rise. No season ever turns it from summer to winter, because there is no orbit to carry it through one. The nearest true starlight would reach it only as a faint scattering of distant, unfamiliar points, no brighter, no warmer than the stars scattered across your own night sky, offering it nothing in the way of heat or day. Whatever weather that world carries, whatever storms move through whatever atmosphere it holds onto, unfold in a darkness that never breaks, on a world with no morning to look forward to and no evening to close the day. It has been drifting through that darkness, undiscovered and unremarked upon, for longer than human beings have been recording history, and it will keep drifting through it, entirely unbothered by our having finally noticed it, for a very long time yet to come. Against the crowded backdrop of the galaxy's core, thick with the light of countless ordinary sunlit stars, that one dark world would be utterly impossible to pick out by eye. A single unlit stone somewhere among an entire river of light, noticed at all only because, for 2 brief days, it happened to pass in front of exactly the right star, at exactly the right angle, for anyone on Earth to see the effect of its passing. Given where that mass falls, comfortably within the range planets typically reach while still growing inside the swirling disk of gas and dust that surrounds a young forming star, rather than the far greater mass a failed star would need to ignite fusion and shine on its own, Dong and his colleagues lean toward a particular explanation for how this world ended up drifting alone, that it once belonged, like the overwhelming majority of planets astronomers have ever found, to a system built around its own star, until something disturbed that arrangement badly enough to throw it out into the dark for good. Perhaps a close pass by a sibling planet sent it tumbling outward past the point of no return. Perhaps the gravity of some other star, wandering too near the young system in its earliest, most chaotic years, reached in and pulled it loose. The mass alone cannot say which. Nothing in the data names the system this planet came from, or the year it left, or the precise event that set it loose. What the numbers support is a profile, a reasonable, well-grounded inference rather than a witnessed history, and it is worth being honest about that difference, because the line between what has actually been measured and what has only been reasonably inferred sits at the very center of this entire story. It is a strange thing to hold in mind at once how very small this result is and how very large its implications might be. One planet, one measured mass, one measured distance, set against a galaxy that may hold billions of worlds like it, drifting unlit and largely uncounted. A single confirmed case can feel almost modest. One name added to a census that is otherwise still built entirely out of statistics and probability, and yet it represents something that, for the better part of 3 decades, had simply never been achieved. Proof, not statistical assertions but direct, physical proof that a specific, individual world, with no sun of its own, is exactly where the numbers say it is, carrying exactly the mass the numbers say it carries. Everything this field has claimed about starless planets before now, the population estimates, the upper limits, the hints of smaller worlds hiding in even briefer flickers, has rested on statistics, careful, honest, hard-won statistics, but statistics all the same, describing a crowd rather than naming a single member of it. This is the first time the crowd has produced one individual member, confirmed and held up to the light. And that success, as satisfying as it is, only sharpens the question sitting underneath everything explored so far. The comfortable explanation, the one that fits this newly measured world so neatly, is that it was cast out, flung from a system that once held it, the way every familiar planet is still held today. It is a tidy story, and for this particular world, the evidence genuinely does point that way. But tidy stories have a way of getting generalized further than the evidence actually allows, applied to an entire population on the strength of a single well-explained case. Somewhere, out past the reach of any one star's gravity, astronomers have also found stranger things than a single planet cast loose and drifting, worlds that appear to have never belonged to a star at all. Not once, not briefly, not at any point in their history. Whether being thrown out is truly the whole story, or only the more familiar half of it, is a question the numbers alone, however carefully measured, cannot yet answer. To answer that question honestly, it helps to slow down and look at what being thrown out of a planetary system actually involves. Because ejection, however easily the word gets reached for, is not some vague, catch-all explanation. It is a specific, well-understood, and thoroughly ordinary piece of celestial mechanics, one that astronomers can model, predict, and watch unfold in simulation after simulation, and one that has almost certainly played out inside a great many of the planetary systems that have ever formed, including, in its own quieter way, our own. Understanding exactly how it happens turns out to matter a great deal, because it is the only way to know where that explanation eventually runs out. A young planetary system, in its first few tens of millions of years, is not the calm, orderly arrangement we tend to picture when we look at a diagram of orbits in a textbook. It is closer to a crowded room, still finding its seating. Planets are still growing, still migrating inward and outward through the disk of leftover gas and dust that built them, their orbits not yet settled into the long, stable, well-spaced paths they will eventually follow for billions of years. In a system that happens to form several massive planets close together, gravity keeps tugging every orbit slightly out of true, and every so often, 2 of those orbits drift close enough for one planet to feel the other's gravity strongly, briefly, and dramatically. Picture a game of pool at the exact moment the rack is broken. The cue ball strikes the cluster, and while most of the other balls scatter only a short distance before settling, one of them, struck at just the wrong angle, goes flying clean off the table. In a planetary system, the table has no rails. A planet struck hard enough by a close pass from a giant neighbor does not slow down and settle into a new orbit further out. It simply keeps going faster than the star's gravity can ever pull it back, out past the edge of the system and into the open dark beyond. Astronomers who build computer models of young planetary systems see this happen routinely, almost as a matter of course, whenever a system begins with several giant planets crowded close together. Ejection, in these simulations, is not the exception. It is very often the mechanism by which a young, overcrowded system settles down at all, flinging away its most disruptive member so the rest can finally find stable, lasting orbits. The evidence is not only theoretical. Astronomers studying planets around other stars have found a striking number of giant worlds in tight, scorching orbits that any calm, orderly process of formation should never have produced, some of them circling their star backward, against the direction the star itself spins, a kind of orbital signature that is very difficult to explain, except as the aftermath of a violent, unsettled youth. One planet's path bent and twisted by a close, disruptive encounter with another. These worlds did not necessarily leave their systems entirely. Some were merely rearranged, thrown into strange, tilted new orbits, rather than thrown out altogether. But the same rough gravitational handling that tilts one planet's orbit can, given a slightly harder shove, send a different planet out of the system for good. Astronomers studying the wide, dusty rings of debris that surround many young stars, the leftover rubble from planet formation that never quite finished clumping into worlds of its own, have found some of these rings warped, clumped unevenly, or tilted at odd angles relative to the star's own rotation, patterns that make far more sense as the lingering aftermath of a large planet's disruptive passage through the disk than as anything a calm, undisturbed system would ever produce on its own. Taken together, the tilted orbits and the disturbed rings tell much the same story from two different angles. Violence of exactly this kind has left its signature scattered across a great many young planetary systems, not just our own suspected history, and not just the single measured world described earlier, but seemingly as an ordinary, recurring feature of how planetary systems settle into their final, stable shapes. Some dynamicists studying our own solar system's early history have proposed that it may have gone through something similar. The outer planets we know today, Jupiter, Saturn, Uranus, and Neptune, did not necessarily form in the orbits they now occupy. A well-studied model of the solar system's youth suggests they migrated substantially before settling where we find them, disturbing the orbits of countless smaller bodies along the way. In an episode, some researchers connect to the ancient bombardment, scars still visible on the surface of the moon. A few researchers have gone further still, proposing that our system may once have held a fifth giant planet that got too close to the others during that upheaval and was thrown out entirely, leaving no trace behind but the disturbed orbits of everything that remained. It remains a genuinely open hypothesis, argued over by specialists rather than settled among them, but it is a useful reminder that ejection is not some exotic fate reserved for distant, unlucky worlds. It may well be a normal chapter in the biography of ordinary planetary systems, including, quite possibly, the one that raised you. Given how common this process appears to be, it would be entirely reasonable to assume it explains every starless world astronomers have ever found. And for a great many of them, the evidence really does point that way, the planet described earlier among them. But in 2023, a survey of a very different kind, using a very different instrument, turned up a population of free-floating worlds that this same, well-understood mechanism struggles to account for. And the trouble is not with the numbers involved. It is with something stranger. Some of these worlds were found in pairs. The discovery came out of one of the most closely studied patches of sky in all of astronomy, the Orion Nebula, a vast, glowing nursery of gas and newborn stars, visible even to the naked eye as a soft smudge below the three stars of Orion's belt. It sits roughly 1,300 light-years from Earth, close enough, by galactic standards, to study in extraordinary detail, and young enough, at only a little over 1 million years old, that the stars and planets forming inside it are still actively being born rather than long finished. Astronomers have pointed telescopes at this nebula for the better part of 2 centuries, and it remains, even now, one of the very best places in the galaxy to watch star and planet formation unfold in something close to real time. Its glowing gas lit from within by the fierce young stars already blazing at its heart. Mark McCogrian, a senior science advisor at the European Space Agency, had wondered for decades just how small an object that nebula might be hiding. Back in 2000, working with the Hubble Space Telescope, he had gone looking for the faintest, lowest mass objects the nebula's crowded, dusty core might contain, curious how far down the scale of planetary and stellar mass nature was actually willing to go. Hubble, for all its power, could only see so deep into a nebula thick with obscuring dust, and the search turned up little more than tantalizing hints. It took the far greater sensitivity of the James Webb Space Telescope, launched decades later and built specifically to see in the infrared light that slips through dust an ordinary telescope cannot penetrate, and a survey McCogrian led together with his colleague Samuel Pearson, published in 2023, to finally answer the question he had first asked at the start of the century, and the answer was stranger than either of them had expected. The survey relied on the telescope's near-infrared camera, an instrument sensitive enough to pick out objects far too faint and far too cool for Hubble to have ever noticed. Patiently imaging the same crowded stretch of nebula McCogrian had first tried to probe more than 2 decades earlier. Scanning the nebula's crowded core, Pearson and McCogrian's survey turned up more than 500 free-floating, planetary mass objects, none of them orbiting any star, each one drifting through the nebula on its own. That alone would have been a significant discovery, a striking confirmation that unattached, planet-sized worlds really do form, and form abundantly, inside a young star cluster, adding real, direct imaging weight to what the microlensing surveys elsewhere in the galaxy had only ever suggested statistically. What made the survey remarkable was what turned up among that larger crowd. Somewhere around 40 of these objects were found not drifting alone, but paired off, 2 planetary mass bodies orbiting a shared center of gravity the way a pair of ice skaters, holding hands, spin slowly around a fixed point between them rather than one leading and the other simply following. A couple of triple systems turned up as well, 3 such worlds bound loosely together. Astronomers gave the pairs an almost affectionate nickname, Jupiter Mass Binary Objects, or Jumbos for short, and the mass of the individual members, everywhere, from well under Jupiter's own weight up to somewhere around 14 times that, placed every one of them, paired or solitary, comfortably within what anyone would ordinarily call planetary territory, not stellar. Their separations were equally striking. Some pairs orbited one another at roughly the same distance Neptune keeps from our own Sun, while others drifted more than 10 times farther apart still, bound together across a gulf of space that would swallow our entire solar system many times over, confirming that any 2 of these faint, distant points of light were actually bound to each other, rather than simply 2 unrelated objects that happened to appear close together in the sky, purely by chance, from Earth's particular vantage point. Took its own kind of careful, patient work. The test astronomers reach for in situations like this is motion. 2 truly paired objects, locked together by their mutual gravity, will drift across the sky together over time, tracing out matching paths, the way 2 dancers moving in step remain a fixed distance apart, no matter how the music carries them across the floor, while 2 objects, merely lined up by chance, will drift apart at their own separate paces, revealing the coincidence for what it was, sooner or later. By comparing images of the nebula taken years apart, Pearson and Makorian's team was able to check enough of their candidate pairs against exactly this test, and the pairings held. The objects were not simply sharing a line of sight from our perspective. They were, as best as anyone could determine, genuinely orbiting one another, out in the open dark, unattached to any star. It is worth pausing on the scale of that number for a moment, because it carries an implication easy to miss on first hearing it. The Orion Nebula is a single stellar nursery, one relatively modest patch of the galaxy, home to only a few thousand young stars in all. And yet, it alone appears to have produced more than 500 free-floating, planetary mass objects in the course of its brief, million-year existence so far. The Milky Way holds many thousands of nurseries like it, some larger, some smaller, scattered across every spiral arm, forming new stars and, evidently, new unattached worlds continuously, and has been doing so for more than 10 billion years. If Orion's productivity turns out to be anywhere close to typical, rather than some unusual outlier, it becomes considerably easier to understand how the statistical population estimates described earlier, however uncertain their exact figures remain, keep landing on numbers this large. A single nursery producing hundreds of starless worlds in barely a geological instant is not, on its own, proof of anything about the whole galaxy. But it does make the idea of a genuinely vast, largely uncounted population feel a good deal less like speculation and a good deal more like ordinary bookkeeping, multiplied out across a galaxy old enough and busy enough to have built stars and their starless cast-offs, alike in numbers no single survey will ever fully catalogue. It is worth being precise about why this troubled astronomers as much as it did, because the trouble was never simply that free-floating planets exist. That much the microlensing surveys had already suggested for over a decade. The trouble was the pairing. Ejection, the well-understood mechanism described earlier, offers no easy explanation for how two planets could be thrown out together, still gravitationally bound to each other across such staggering distances. A single struck ball flying off a pool table is one thing. Two balls flying off together, still spinning gently around one another the whole way, is something else entirely, and it demands a very different kind of explanation. For an ordinary ejection to preserve a bound pair, rather than simply scattering both worlds independently in two different directions, the encounter that flung them would need to thread an extraordinarily narrow needle, violent enough to detach both planets from whatever star or stars they were orbiting, yet gentle enough and precisely angled enough to leave the two of them still bound to each other afterward, rather than torn apart in the process. Most simulations of chaotic planetary scattering simply do not produce that outcome very often. One research team proposed a specific way it might still happen: a close, chaotic encounter between two young, sun-like stars early in the nebula's history, violent enough to strip a bound pair of planets away from one of the stars all at once, launching them outward together rather than separately, the stellar flyby itself supplying exactly the kind of narrow, precisely angled disturbance an ordinary two-planet scattering event could not. It is a careful, mathematically grounded hypothesis, and it remains, for the moment, the leading explanation among researchers who still favor an ejection-based origin for the jumbos. It is also, by its own proponents' admission, difficult to test and difficult to confirm from a single snapshot of a nebula that is, itself, only a little over 1 million years old. The alternative explanation reaches for something altogether different. Not ejection at all, but formation in place, using the same basic process that builds a star, only on a dramatically smaller scale. Stars themselves are born when a cloud of gas and dust, sometimes many times the mass of our Sun, begins to collapse under its own gravity, drawing inward and spinning faster as it shrinks. The way a skater drawn into the center of the ice will pick up speed with arms pulled tight to the body. Given enough starting material, that collapsing cloud eventually grows dense and hot enough at its center to ignite nuclear fusion, and a new star switches on. Astronomers have long known that this same collapse process can, on occasion, fall just short of building a true star, producing instead what is called a brown dwarf, an object first confirmed to exist only in the middle of the last decade of the last century, too small ever to sustain the kind of steady hydrogen fusion that powers a star like our Sun, destined instead to spend its entire existence slowly cooling and fading, dimmer with each passing million years, rather than shining with anything like a star's long, stable light. Brown dwarfs, once confirmed, filled in a real and useful category between star and planet, typically weighing somewhere between about 13 and 80 times the mass of Jupiter. Estimating the mass of a young, still glowing object like this from its brightness alone depends on knowing its age, since a newly formed world, or brown dwarf, still carries the leftover heat of its own collapse and glows brighter for a time than an older object of the very same mass ever will. Only as millions of years pass does that leftover warmth fade, and the true fainter brightness that matches its actual weight finally emerges. Because the Orion Nebula's objects are all still extremely young, barely a little over 1 million years old, astronomers were able to use that youth to their advantage, comparing each object's brightness and color against models of how a still cooling world of a given mass ought to glow at exactly that age. And it was this careful accounting for youth that allowed the survey to place the jumbos so confidently below the usual planetary and brown dwarf mass boundary, rather than simply guessing at their weight from brightness alone. For years, the working assumption was that the same collapse process had a firm lower limit, close to the low end of the brown dwarf range, below somewhere around 3 to 7 times the mass of Jupiter. A shrinking cloud of gas simply could not hold itself together long enough to condense into anything at all. It would disperse before it ever became a discrete object, the way a loaf of bread made with too little flour never quite rises into a loaf, spreading instead into a thin, shapeless crust across the pan. The jumbos sit well below that supposed floor, some of them at only a fraction of Jupiter's own mass, and yet there they are, distinct, individual, gravitationally bound objects, several of them paired off exactly the way a binary star system pairs off, only in miniature. If they truly formed this way, through direct collapse rather than ejection, it would mean the same process that builds the Sun and every other star in the night sky, and every brown dwarf besides, is capable of producing something dramatically smaller than anyone had previously thought possible, blurring a boundary astronomers had long assumed was reasonably firm. One proposed explanation for how nature might manage this involves a process with a far less poetic name, photoerosion. The astronomer Richard Parker at the University of Sheffield, along with several colleagues, has modeled in detail how this might work inside a nebula as crowded and violent as Orion's. The nebula is not a quiet, undisturbed nursery. It sits close beside some of the hottest, most massive young stars in the entire region, stars that pour out enormous quantities of ultraviolet radiation, the same general kind of light that causes sunburn, only at an intensity almost impossible to picture standing here on Earth. Under conditions like that, a small, loosely bound clump of collapsing gas, one that might otherwise have simply dispersed on its own, could instead find its outer, looser layers stripped and boiled away by that fierce nearby radiation, the way a steady, relentless wind can carve a soft, crumbling rock formation down into something smaller, harder, and more compact than it began, wearing away everything that cannot hold its shape and leaving only the densest core standing. What is left behind, according to this idea, is a leaner, denser core, still massive enough to hold itself together as a single body, but only because the radiation from its stellar neighbors trimmed away everything that could not survive it. Parker's models suggest that under the right conditions, this kind of radiation-driven trimming really could push a collapsing cloud's final mass down into the planetary range, well below the old theoretical floor. It is a genuinely elegant hypothesis, tying the jumbo's small size directly to the violent, radiation-soaked environment they were found in, and it has real support from researchers modeling the physics in detail. It has not, however, settled the question. Both the close flyby ejection idea and the photoerosion collapse idea remain live possibilities, argued over in the scientific literature as this video is being made, and it would be dishonest to present either one as the final word. There is a smaller, quieter argument tangled up inside this larger one, and it concerns something as basic as what to call these objects in the first place. In 2006, the world's astronomers gathered at a general assembly and, in a decision still remembered well beyond the scientific community, voted on a formal definition of the word planet, a decision that famously reclassified Pluto, a world every American schoolchild had grown up counting as the 9th planet, as something else entirely, a dwarf planet, based on a technical requirement that Pluto had never quite met. Among the requirements in that same definition is a simpler one, rarely discussed in all the fuss over Pluto. To be a planet, a body must orbit a star. By that same standard, strictly applied, not one of the jumbos, and not the lone drifting world described earlier either, technically qualifies as a planet at all, regardless of size, regardless of composition, regardless of how closely it resembles Jupiter or Saturn or any other familiar world. Many working astronomers use the word rogue planet anyway, comfortably and without much fuss, because it is the phrase the public already understands, and because insisting otherwise in casual conversation solves nothing. But in careful, technical writing, you will often see a more cautious phrase instead: planetary mass object, a label that describes what something weighs without making any claim at all about what it is, or where it came from, or whether it has ever belonged to anything. It is a small, almost bureaucratic distinction, the kind of thing that might remind you of a town zoning office trying to decide which permit applies to a building nobody quite anticipated when the rules were first written, but it points at something real. Astronomers are not simply arguing over a word. They are admitting, honestly, that the jumbos sit in a genuine gap in the map, a category that existing definitions never anticipated, because nature, once again, turned out to be stranger and more varied than the tidy categories built to describe it. Taken together, these two competing explanations suggest something worth sitting with for a moment. The population of worlds, drifting through the galaxy with no star to call their own, may not be one population at all, but at least two, wearing the exact same disguise. Some of them, like the Saturn-class world whose mass and distance were finally pinned down earlier, most likely did belong to a star once, until gravity's rougher edges threw them out into the permanent dark. Others, like at least some of the jumbos, may never have belonged to anything, born the way a star is born, simply too small and too faint ever to ignite, orphans in the loosest sense only, since an orphan first has to have had a home to lose. From the outside, drifting alone through the vast, cold spaces between the stars, the two kinds of worlds would look identical: dark, silent, undetectable by any means except the same gravitational flicker that first revealed their solitary cousins. It may be, in fact, that most starless worlds are neither purely one story nor the other. A planet ejected from a young, still-forming system would have been flung out alongside plenty of raw material still clinging to it, gas and dust that never finished settling into a proper planetary disk, so that even an unambiguously ejected world might carry the faint fingerprints of formation processes closer to a miniature stars than anyone would expect from a planet's simple, tidy origin story. And a world born through direct collapse, cooling alone in the dark since its birth, would still obey every ordinary law of planetary physics once it existed, indistinguishable in composition and behavior from a proper, ejected planet of the same mass and age. There may even be a middle category astronomers have not yet cleanly separated out at all, a small, failed clump of collapsing gas that never quite grew large enough to stand entirely on its own, only to be caught up afterward in the same rough gravitational shuffling that ejects ordinary planets, thrown outward a second time before it ever had the chance to settle. Sorting out which of these paths any single object actually followed, using nothing more than a brief flicker of borrowed starlight or a faint infrared glow recorded from many trillions of miles away, may prove to be one of the more stubborn puzzles this field faces in the years ahead. Which leaves a question that neither the ejection story nor the direct collapse story has yet managed to answer, and one that matters rather more than it might first appear. Whatever brought a given world into its starless existence, ejection or birth in isolation, that world still has to be made of something. It still carries whatever internal structure, whatever leftover heat, whatever restless geology it was born with or has generated since, sealed away now behind a darkness that will never again be interrupted by sunrise. A planet is never simply the story of how it came to be where it is. It is also, and perhaps more importantly, everything still happening within it, long after the story of its origin has finished playing out and been half forgotten. The question worth asking next, then, is not where these worlds came from, a question this hunt has only partly answered, but what, if anything, might still be happening inside one of them, deep beneath a surface no star has ever warmed. The question worth asking next, then, is not where these worlds came from, a question already explored at some length, but what, if anything, might still be happening inside one of them, deep beneath a surface no star has ever warmed. And the honest answer begins with a fact easy to overlook, precisely because it is so ordinary. Warmth on any planet, rocky or icy, giant or small, has never depended entirely on a nearby star to begin with. Every planet, whether it still circles the star that raised it or drifted free of one long ago, carries its own private furnace sealed inside it since the moment it first came together, and that furnace does not switch off simply because the planet in question has drifted out of reach of any sun. Understanding what that quiet, hidden furnace can and cannot do on its own, and what it might manage with a little help besides, is the whole of what follows, and it begins, fittingly enough, not out among the stars at all, but with ordinary rock. That inner warmth comes from two sources, both of them old, both of them thoroughly ordinary, and neither of them requiring starlight at all. The first is simply leftover heat from birth. A planet does not assemble itself gently. It grows by collision, smaller, rocky and icy bodies slamming together again and again over millions of years, each impact converting the raw energy of motion into heat, and a young planet, freshly formed, is left glowing with the accumulated warmth of its own violent childhood. Heat that then takes a very long time, often billions of years, to finally leak away into space. The second source is quieter, steadier, and considerably longer lived. Certain elements locked inside a planet's rock and metal, uranium and thorium, and a radioactive form of potassium among them, decay slowly over time, releasing a small, continuous trickle of heat as they do, the way a dying ember, banked carefully under ash overnight, keeps a fireplace faintly warm until morning, without any fresh log ever being added. This radiogenic heat, as it is called, has been quietly warming the inside of our own Earth for the planet's entire 4.5 billion year history, driving the slow churn of its molten interior, powering its volcanoes, and keeping the deep rock beneath your feet, at this very moment, considerably warmer than the air above it. Scientists have even managed to measure this radioactive warmth directly, not by drilling down to it, which no instrument could survive at those depths and temperatures, but by catching the nearly weightless particles called neutrinos that radioactive decay releases as a byproduct, streaming upward through solid rock as easily as light passes through a window pane. Detectors built deep underground, shielded from interference by the very rock above them, have counted these particles arriving from below in large enough numbers to confirm, directly and quantitatively, that radioactive decay inside our own planet is real, ongoing, and every bit as significant a source of heat as geologists had long assumed it to be. Every rocky planet ever built almost certainly carries at least some version of that same slow, radioactive warmth, sun or no sun, star or no star, entirely independent of anything shining overhead. It helps, before reaching all the way out to a starless world 9,800 light-years distant, to look first at proof already sitting inside our own solar system, close enough to have been photographed in detail. Saturn's small, icy moon, Enceladus, receives only the faintest trace of warmth from the sun at its enormous distance, nowhere near enough to keep anything liquid on its own. And yet, when NASA's Cassini spacecraft flew close by it, again and again, over more than a decade of exploring the Saturn system, it found towering geysers of water vapor and ice erupting from cracks near the moon's south pole, plumes rising so high they could be traced from orbit, fed by a genuine, confirmed, liquid ocean sloshing beneath miles of solid ice. The heat keeping that ocean liquid comes not from the sun at all, but from the moon's own restless gravitational relationship with the giant planet it orbits, flexed and squeezed with every trip around Saturn the way a paperclip, bent back and forth again and again in your hand, will grow noticeably warm at the point where it keeps folding, friction generated entirely from repeated motion rather than from any outside source of heat. Jupiter's fiery moon Io tells much the same story from the opposite direction. Instead of hiding an ocean, it vents its internal heat outward through hundreds of active volcanoes, the most volcanically violent body anywhere in the solar system, driven by that same relentless gravitational flexing rather than by sunlight, which barely reaches it at all. A third Jovian moon, Europa, sits somewhere between the two, its cracked, icy shell hiding an ocean scientists suspect may hold more liquid water than every ocean on Earth combined, kept from freezing solid by that same tidal flexing. A discovery owed largely to the Galileo spacecraft's long study of the Jupiter system in the final years of the last century. Between these three small, icy, and rocky worlds, none of them warmed in any meaningful way by the distant sun, the evidence stands confirmed and photographed rather than merely proposed, gathered patiently across decades of careful spacecraft observation. A body can be warm, wet, and geologically alive at almost any distance from a star, provided it has some other steady source of energy working on it from within. A fully unattached, starless world has no larger planet to orbit, and so it has no equivalent to Enceladus's flexing, no paperclip being bent back and forth by a nearby giant's gravity. Whatever warmth such a world carries would have to come from the quieter of the two sources described earlier, the slow radioactive trickle rather than the friction of tidal flexing, and on its own, that trickle is a modest thing, nowhere near strong enough to keep an exposed, airless surface anywhere close to the melting point of ice in the deep cold of interstellar space, a cold far more severe and far more unrelenting than anything even the harshest winter on Earth ever produces. For a starless world to hold onto any real warmth at its surface, something else would have to be doing quiet work alongside that faint, steady trickle from within, something capable of trapping what little heat there is, rather than letting it bleed away into the dark. In 1999, the planetary scientist David Stevenson at the California Institute of Technology proposed exactly such a mechanism in a paper he was careful, even at the time, to describe as speculative, a word he used deliberately, aware of how far his idea reached beyond anything then confirmed. Stevenson's proposal turns on the peculiar behavior of hydrogen gas under enormous pressure, a large enough rogue planet, one that formed with a deep primordial envelope of hydrogen wrapped around it, the same basic material Jupiter is made of, would hold onto that atmosphere for the whole of its existence, gravity alone being more than sufficient to keep such a light gas from drifting off into space, even with no star nearby to strip it away. Near the base of a hydrogen atmosphere thick enough and under pressure high enough, something changes in how that gas interacts with heat. Crushed close together under such enormous weight, hydrogen molecules collide far more often than they would drifting loosely through a thin, ordinary atmosphere, and each of those collisions briefly changes how the gas absorbs infrared light, broadening its ability to catch and hold outgoing warmth across a wider range of wavelengths than the same gas would ever manage at ordinary pressure. It is not so different in its basic effect from what already happens on Venus, a genuinely scorching world despite clouds that reflect away most of the sunlight that reaches it, its surface kept far hotter than an oven. Crushing atmosphere traps outgoing heat so effectively that almost none of it escapes back into space. Venus achieves that trapping with carbon dioxide rather than hydrogen, and with plenty of direct sunlight streaming in to begin with, two significant differences from anything a starless world would have working in its favor. But the underlying principle that a sufficiently thick, sufficiently pressurized atmosphere can hold heat in far more stubbornly than a thin one ever could is the same principle Stevenson leaned on, applied instead to a world with no incoming sunlight at all, relying only on its own faint internal warmth rather than in nearby stars. Picture an old vacuum flask, the kind that once sat on nearly every kitchen counter, keeping coffee hot for hours on a cold morning, not by adding any new heat of its own, but simply by trapping the heat already inside and refusing to let it escape through its sealed, insulated walls. A dense enough hydrogen envelope, under Stevenson's proposal, could behave in something like that same way, not generating warmth, but holding on to whatever faint, steady trickle of radiogenic heat the planet's interior already produces, preventing it from radiating away into space as quickly as it otherwise would. Trap enough of that heat for long enough, and the math, at least on paper, suggests a surface warm enough, even at the very bottom of that thick, hydrogen-heavy atmosphere, to allow liquid water to persist, sealed away far beneath skies that will never once brighten with a sunrise. It is worth returning for a moment to Stevenson's own caution here, because it matters. His proposal was, and remains, a calculation built from established physics, not a confirmed observation of any real place. No telescope has ever measured the atmosphere of an actual rogue planet closely enough to test whether this kind of pressure-driven warming genuinely occurs in nature the way the mathematics suggests it should. Other researchers who examined the idea in the years afterward raised real technical objections of their own, questioning whether such a planet could realistically hold onto a hydrogen envelope thick enough for the effect to matter across the full span of billions of years. Given the slow, steady stripping that gradually erodes away at any planet's atmosphere over such enormous stretches of time, one molecule at a time, whether from the faint but ceaseless pressure of interstellar radiation or from the planet's own outermost, thinnest layers slowly leaking away into the vacuum around it. The hypothesis has survived this scrutiny reasonably well, refined and adjusted rather than discarded. But it remains exactly that, a hypothesis, a genuinely serious one, grounded in real physics, but a proposal about what might be possible rather than a report of what has actually been found. Not every starless world, of course, would have formed massive enough to hold onto a deep hydrogen envelope in the first place. Smaller, rockier worlds, closer in size and composition to Earth than to Jupiter, call for a different version of the same basic idea, one that a pair of researchers at the University of Chicago, Dorian Abbott and Eric Switzer, worked out in careful detail in 2011. Rather than a thick blanket of hydrogen gas, their proposal leans on something far more familiar: ordinary ice, layered thick enough to do the same essential job insulation always does, holding heat in rather than letting it escape. Farm families across the middle of the last century understood this same basic principle without ever needing to name it, and put it to work in both directions at once. A root cellar, dug down into the earth and covered over with packed soil, stays measurably warmer through a brutal winter than the air directly above it, not because anyone lit a fire down there, but because the earth itself holds a slow, steady warmth of its own, and a thick enough covering keeps that warmth from simply escaping upward into the winter air. The very same families, come summer, relied on the opposite trick to the same underlying end: an insulated ice house, packed with blocks of ice cut from a frozen pond months earlier and buried in sawdust or straw, could keep that ice from melting clean through a hot summer, insulation this time working to hold the outside world's heat at bay rather than to keep an inner warmth from escaping. Both buildings ran on precisely the same physical principle: insulation slowing the flow of heat across a boundary, only pointed in opposite directions. Abbott and Switzer's proposal, which they named the Steppenwolf scenario after the wandering solitary creature of the same name, borrows the root cellar's direction rather than the ice house's, using ice itself, insulated further still by frozen gases trapped within it, over a rocky, Earth-like world's own faint, steady inner heat. Layer that insulation thick enough over a planet's own patient radioactive warmth, and their calculations suggest a liquid ocean could persist beneath it indefinitely, sealed away from a sky that offers no warmth of its own to help. This is not, as it happens, a purely theoretical picture. Even here on Earth, beneath nearly 2.5 miles of solid Antarctic ice, sits Lake Vostok, a body of liquid water roughly as deep as a modest lake anywhere else in the world, and stretching for dozens of miles beneath the ice sheet above it, kept from freezing solid only by the slow warmth rising from the rock beneath it, the very same radiogenic heat described earlier. sealed in by an ice sheet thick enough to hold that warmth in rather than let it bleed away into some of the coldest air found anywhere on the planet's surface. Air that can fall to temperatures no unprotected, liquid water could ever survive. Nothing about Lake Vostok required starlight to stay liquid. It required only insulation and a steady, patient source of heat from below, precisely the two ingredients the Steppenwolf scenario proposes for a starless planet drifting far beyond the reach of any sun at all. A rogue world of Earth-like composition and age, Abbott and Switzer calculated, could in principle maintain a subglacial ocean not for mere centuries, but for timescales stretching into the billions of years, powered the entire while by nothing more than the same slow radioactive decay already quietly warming the rock beneath Antarctica today. There is a further wrinkle to this picture, one that has only recently drawn serious attention, reported only a few months before this video was made. A starless planet need not necessarily be entirely without a partner of its own. Just as our own moon formed alongside Earth and has remained bound to it ever since, a planet ejected from its birth system, or one that formed in isolation from the very start, could plausibly carry a moon or moons along with it, bound by their mutual gravity, even as the pair together drifts free of every star. Researchers, working with a German research initiative called Origins, associated with the Max Planck Institute for Extraterrestrial Physics, modeled recently what such a pairing might mean for warmth, and the results suggest something genuinely encouraging for the prospects of a liquid ocean surviving over truly enormous stretches of time. A large moon, tugged and flexed by its companion planet's gravity across every orbit the two make around their shared center of mass, would generate exactly the kind of frictional, tidal heat Enceladus generates from Saturn, the bent paperclip warmth described earlier, except here supplied not by any star, but by the planet and moon's ongoing gravitational relationship with each other. A relationship that, unlike a lone world's fading radiogenic trickle, does not weaken meaningfully over billions of years, so long as the orbit itself remains even slightly uneven rather than perfectly circular. Combine that tidal flexing with a hydrogen-rich atmosphere trapping the resulting warmth in place, and the team's modeling suggests such a moon could plausibly sustain a liquid ocean for upward of 4 billion years, roughly the entire age of life on Earth so far. All of it powered by nothing more than two starless worlds bound together, quietly warming each other in a darkness that no sunrise will ever interrupt. There is something worth sitting with in that image, a moment longer than the physics alone strictly requires. A planet with no sun may still, in a real and physical sense, not be entirely alone, carrying its own small, private companion through the dark, the two of them generating between themselves precisely the warmth that no star was ever there to provide. It is worth being precise about where this leaves the population of starless worlds described earlier in this hunt, because not every one of them would necessarily fit either version of this picture equally well. The single planet, whose mass and distance were measured directly earlier, is understood from its mass alone to be a gas giant broadly comparable to Saturn, a world built more along Stephenson's hydrogen-blanketed lines than Abbott and Switzer's icy, rocky ones, assuming it holds onto an atmosphere thick enough for the mechanism to apply at all, which remains unconfirmed. A world of that size and composition, if the hypothesis holds, would carry its water, if any, not as a familiar surface ocean, but sealed away far beneath crushing layers of gas. A very different picture from the shallower, more Earth-like ocean The Steppenwolf scenario imagines beneath a rocky world's ice the far fainter, far harder to detect population of smaller, Earth-sized, starless worlds hinted at in the same statistical surveys that first suggested giant rogues might be common are the more natural candidates for a genuine Steppenwolf-style ocean, precisely because their size and likely composition sit closer to Earth's own, close enough that the same rock, the same radioactive elements, and quite possibly the same water ice that built our own solar system's rocky worlds could plausibly have gone into building them as well. The paired, gravitationally bound worlds explored earlier, wherever their own masses happen to fall along that same spectrum, would in principle be eligible for either version of this picture too, warmed either by a thick hydrogen blanket or by insulating ice, depending on which formation story, if either, actually produced them. One more open thread this hunt has not yet managed to tie off. Both possibilities remain, for now, exactly that, possibilities, grounded in solid physics and, in Lake Vostok's case, in something already observed and confirmed right here at home, but never yet tested against a single real measurement taken from an actual starless world light years from Earth. Closing that gap, at least on the level of statistics, if not yet on the level of individual worlds, is precisely the task a new instrument has been built to take on. A new space telescope, named for Nancy Grace Roman, the astronomer whose early advocacy helped bring the Hubble Space Telescope into existence decades ago, is now, at the time this video was made, expected to launch within the coming weeks, joining an earlier space telescope already stationed far out past the Moon's orbit. Its central survey for this kind of hunt carries a plain descriptive name, the Galactic Bulge Time Domain Survey, and its entire purpose is exactly what that name suggests: watching the crowded, star-choked bulge at the galaxy's center, over and over, patiently, for months on end, where the ground-based surveys described earlier in this hunt must contend with a shifting, turbulent atmosphere overhead, one that blurs and dims the very short, very faint flickers a small, low-mass rogue planet produces. This new observatory will watch the same crowded stretch of the galaxy's core from the steady vantage point of space itself, uninterrupted by weather, uninterrupted by daylight, uninterrupted by anything at all, for months at a stretch. Its wide field of view, covering roughly 100 times more sky in a single image than its most capable predecessor, and its ability to watch several 100 million stars simultaneously rather than the tens of millions the ground-based surveys manage, should allow it to catch far more of the short, faint signals that smaller, Earth-sized starless worlds produce, the very same ultra-short flickers that earlier surveys could only barely detect and never fully confirm. It would be dishonest, however, to suggest this new instrument will settle the deeper question raised in this section. A microlensing survey, however powerful, however much more sensitive than everything that came before it, can only ever measure a brief flicker of borrowed starlight, revealing a planet's rough mass, and, with the right follow-up observation, its distance, the way the earlier hunt for one confirmed world demonstrated so clearly. It cannot look inside that planet, cannot sample its atmosphere, cannot detect a hidden ocean sealed away beneath miles of ice on a world thousands of light years distant, and it was never designed to try. What this new survey stands to offer is a far better census, a far more confident answer to how common small, starless, rocky worlds like the ones Abbott and Switzer imagined actually are scattered across the galaxy, replacing the wide, uncertain ranges described earlier in this hunt, with numbers drawn from many more confirmed detections, rather than a small handful of statistical hints. That census matters more than it might first seem, because every one of the physical arguments walked through here, the hydrogen blanket, the insulating ice, the possibility of a warming companion moon, only becomes meaningful at scale if starless worlds of the right size and composition genuinely turn out to be common rather than rare. Whether any of them genuinely keep an ocean liquid beneath their ice, whether Stevenson's hydrogen blanket genuinely works the way his mathematics suggests it should, are questions that will likely wait for instruments not yet built, telescopes capable of studying a starless planet's faint infrared glow directly rather than only the brief shadow its gravity casts. A world genuinely holding warmth beneath an insulating shell, whether ice or hydrogen, would radiate at least a faint trace of that trapped heat back out into space, a whisper of infrared light distinguishing it, at least in principle, from a truly dead, uniformly frozen stone of the same size and distance. And yet, even without that final confirmation, something has already shifted simply by walking carefully through what is and is not physically possible. A planet with no sun was, not so very long ago, imagined as little more than a dead frozen stone, tumbling through absolute darkness with nothing whatsoever happening inside it. The physics explored here suggests something considerably less bleak and considerably more interesting, that warmth, water, even the slow, patient churn of a living geology may not require a star at all. Only the ordinary, ancient heat every rocky world is born, carrying within it, and, in some fraction of cases, the right kind of blanket, whether hydrogen gas or ordinary ice, to keep that heat from slipping away. None of this amounts to a clate about life itself. Liquid water is only ever one basic ingredient among several that scientists look for when they ask whether a place could, in principle, support life as it is understood here on Earth. And no rogue planet has ever been examined closely enough to say anything at all about what, if anything, its water might hold. What can be said, carefully and honestly, is narrower and in some ways stranger, that the basic physical conditions for liquid water, warmth trapped rather than warmth received, appear to be well within reach for at least some share of these starless worlds, using nothing more exotic than processes already confirmed, photographed, and measured right here in our own solar system. If even a modest share of the vast, still uncertain population of starless worlds scattered across the galaxy fit this description, then hidden beneath the permanent night this entire hunt began with, there may be far more warmth and far more water, quietly persisting than the simple word darkness would ever suggest on its own. What that might mean for how common a genuinely ordinary place like Earth truly is, and for how this galaxy's other, more familiar worlds ought to be understood against everything just described, is where this hunt turns next. What that might mean for how common a place like Earth truly is, deserves to be taken seriously rather than waved away as an idle curiosity, because the honest answer runs against nearly every assumption built quietly into the way most of us have always pictured a planet. Ask almost anyone of any age to sketch a planet from memory, and they will draw, without a moment's hesitation, a circle tracing a path around a star. That single image, a world in devoted, endless orbit around a fixed point of light, has stood for so long as the obvious, unremarkable default that it rarely occurs to anyone to ask whether it actually is the default, or merely the version of a planet human beings happened to be standing on when they first started asking the question at all. It is worth remembering, too, that the question could not even have been asked in any serious way until quite recently. For nearly the entire span of human history, the very idea of a planet implied a star to circle. Nothing else had ever been observed, and so nothing else was ever imagined. The assumption was never stated outright, because it never needed to be. It simply sat underneath every drawing, every model, every textbook diagram, unnoticed in exactly the way the most basic assumptions usually are. Everything walked through so far in this hunt suggests, carefully and without exaggeration, that the picture may run the other way entirely. A galaxy old enough and busy enough to have built hundreds of billions of stars has, in the ordinary course of building them, also flung loose or grown independently a population of unattached worlds that current evidence, however far from a finished census, consistently suggests is large, and quite possibly larger than the population still faithfully circling a star. Some of them, the evidence increasingly suggests, were never flung from anywhere at all, formed instead the way a star forms, never once tethered to anything, orphans, only in the loosest sense of a word that assumes every orphan first had a home to lose. Even the most cautious reading of everything gathered here, stripped of every exaggerated headline and every walked-back estimate, still leaves a population too large to dismiss as a footnote to the more familiar story of orbiting worlds. If the numbers explored across this entire hunt are even approximately right, then a planet quietly orbiting a stable, long-lived star, the way Earth has for 4.5 billion years and counting, is not the ordinary case being politely interrupted by the occasional strange exception. It may be closer to the reverse, the strange exception dressed up by sheer familiarity to look like the rule. There is a particular kind of relationship built into the very word orbit that is easy to take for granted until you try to picture its absence. An orbit is not simply a path through space. It is a commitment, repeated without fail, circuit after circuit, for as long as the arrangement holds. A planet returns and returns and returns again to the same star along the same patient curve, never once drifting far enough to lose the thread. Think of an old compass, the kind that once rode in the glove box of every family car on a long summer drive, its needle swinging this way and that as the car turns a corner, yet always, once the vehicle settles and holds still, drifting back to point the same direction it always has. That fidelity is not decoration. It is the entire reason a compass is useful at all, the needle's willingness to keep returning to one true, unchanging reference, no matter how far the car carrying it happens to wander. A bound planet keeps something like that same fidelity toward its star, forever completing the same devoted circuit rather than drifting off along some path of its own choosing. A starless world has had that needle removed entirely. It still moves, sometimes at considerable speed, but toward nothing in particular, compelled by no fixed point, answerable to no star's patient pull. It simply goes and keeps going, belonging, in the fullest sense of the word, to nowhere at all. This is not, it should be said plainly, a worse way for a planet to exist, only a different one, in the same way that a compass with no needle has not become a worse object than the one it used to be, only an object put to a different use, no longer capable of telling anyone which way is north, but no less real, no less solid, no less there, for having lost the ability. Framed that way, the strangeness of a starless world stops being about darkness, or cold, or distance, the qualities this hunt has spent so much of its time complicating and softening, and becomes instead a strangeness of relationship. What such a world has lost, if it lost anything at all rather than simply never having had it, is not primarily light or warmth, both of which, as the evidence walked through earlier suggests, it may still generate and hold on to in its own quiet way. What it lacks is a center to return to. It has no morning it is owed, no place in a cycle that will bring the light back around after the dark has had its turn. Every planet still bound to a star lives inside a promise of that kind, whether or not anyone standing on its surface ever thinks to notice the promise is being kept. Tomorrow's sunrise on a world like this one is not a small thing. It is the visible proof of an orbit still holding, a commitment still being honored, circuit after circuit, exactly as it has been honored for 4.5 billion mornings already, with no reason on any single one of those mornings that it needed to be so. Nothing about gravity requires a planet's orbit to remain stable across so vast a stretch of time. Systems come apart, sometimes quietly, sometimes violently. Planets get thrown loose, exactly as this hunt has spent so long describing. That Earth's own arrangement has held steady for so long, weathering whatever quiet gravitational disturbances its neighboring worlds have thrown its way across billions of years, is itself a fact worth setting down plainly, without dressing it up as either luck or destiny, simply as one more data point in a much larger pattern this hunt has been tracing from the very beginning. It would be easy, arriving at a thought like that, to turn it into something closer to a lesson than an observation, to tell you, gently, that you ought to feel grateful the next time you happen to catch a sunrise. That is not, in fact, where this is heading, and it is worth being honest about why. Gratitude is a fine thing, but it is yours to arrive at, or not, on your own terms, and it was never the purpose of tracing this particular thread of astronomy to instruct you toward it. Documentaries of this kind are sometimes tempted to close on exactly that note, turning a strange astronomical fact into a tidy piece of advice about how the audience ought to feel about their own lives, and something real is usually lost in that turn, the fact itself quietly replaced by a lesson borrowed from it. What can honestly be said, without overstepping into anything like a lesson, is simply this: the arrangement Earth happens to sit inside, star and planet locked together in a stable, unbroken orbit across billions of years, is very likely one specific outcome among several the universe seems equally willing to produce, and current evidence suggests it may not even be the most common one. That is a fact about the galaxy's demographics, not an instruction about how to spend your evening. What you do with it, if anything, belongs entirely to you. There is a kind of vertigo particular to numbers this large, and it is worth naming plainly rather than letting it pass unremarked. A single confirmed detection, one planet, one measured mass, one measured distance, sits at the near end of a population that may run into the hundreds of billions, and the mind does not naturally know what to do with a ratio like that. It is not unlike standing at the edge of an ordinary town census and being told that the one household you happen to have visited and counted carefully, in full, honest detail, might stand in for hundreds of billions more you will never meet, never see, never have any way of confirming beyond the patient careful statistics that first suggested they existed at all, scattered across a galaxy far too large and far too old for any single survey to ever finish counting. The instinct, faced with a number that large, is often to stop believing it says anything meaningful at all, to let it collapse into an abstraction too big to carry any real weight. That instinct is understandable, and almost certainly universal among anyone who has ever tried to hold a truly large number in mind for more than a moment, watching it slide past the point where it still feels connected to anything real. It is also, this entire hunt has tried to show, not quite fair to the evidence. Each of the revisions traced earlier, the walked-back estimate, The smaller worlds hinted at in briefer flickers, the paired objects that fit no simple story, was not evidence dissolving under scrutiny. It was evidence getting sharper, more careful, more honestly uncertain in exactly the places honesty required it, and less certain nowhere else. It helps, faced with a number too large to hold on to return one last time to the single planet this hunt has kept coming back to throughout, the one whose weight and distance were finally, directly measured, rather than merely inferred. That world has been drifting, unattached and unlit, for a length of time no single sentence can make feel entirely real, though it is worth trying anyway. If it formed alongside an ordinary star-bound system, the way its measured mass suggests it likely did, then whatever event eventually cast it loose almost certainly happened billions of years ago, long before Earth's own surface had cooled enough to hold an ocean, long before anything resembling life had stirred anywhere in this solar system. It was already old, already drifting, already utterly indifferent to the question of whether anyone was watching, when the first single-celled organisms appeared in Earth's ancient seas. It was already old when those first organisms became something more complicated, when the first eyes capable of noticing a night sky at all first opened, when the first human being ever stood upright and happened to glance upward. Every civilization that has ever existed, every fire lit against the dark, every story ever told about the lights overhead, unfolded while that one particular world, and uncountable others like it, went on quietly drifting, exactly as they had been drifting since long before there was anyone to name them. They were not waiting to be found. They had no way of knowing there was anything to wait for. And then, this past January, for the first time in the entire span of that world's existence, someone finally did. Consider, for a moment, how differently this entire hunt might have unfolded had it been undertaken by scientists living on one of the worlds it describes, rather than by scientists living on one of the stars it does not. A civilization arising, somehow, on a rocky world sealed beneath insulating ice, warmed only by its own patient, radioactive heat, would have no sun in its sky to explain, no daily cycle of light and dark to build a calendar around, no obvious, blazing clue pointing toward the existence of other worlds like their own scattered throughout a wider galaxy. Their night, if their planet's frozen surface even allowed for astronomy at all, would show them only the same faint scattering of impossibly distant stars. This hunt has already described drifting past a solitary world 9,800 light-years from here, points of light offering no more warmth or welcome than any other point in an otherwise featureless dark. Such a civilization would have no equivalent of a sunrise to build a myth around, no obvious center to their sky at all, only the same slow wheel of unreachable, indifferent points, turning overhead night after identical night. If their world could even be said to have nights and days as anything other than an arbitrary way of marking time. Whatever early astronomy such a civilization managed to build would necessarily start from a very different question than the one that started this hunt. They would not be asking whether unattached worlds like their own existed. They would be living the answer already, and the far stranger, more speculative question for them would run in precisely the opposite direction, whether, somewhere, out among those same indifferent points of light, a handful of worlds might exist that had somehow kept a star of their own, bound to it in a stable, endless orbit, bathed in a kind of steady daylight their own history had never once given them reason to imagine. It is worth wondering, briefly and without pretending to answer it, whether such a civilization, examining its own sunless sky, would ever think to ask whether a planet like Earth, tethered devotedly to one steady, generous star, might exist at all, or whether an arrangement so different from their own would simply never occur to them as a live possibility. In exactly the same way, an arrangement so different from ours so rarely occurred to us until fairly recently. Two kinds of astronomers on two kinds of worlds, each mistaking their own particular arrangement for the universe's obvious default, each very possibly wrong in exactly the same way, only in opposite directions. None of this requires imagining such a world as entirely without company either, and it is worth returning one final time to a thread raised earlier in this hunt, rather than abandoning it here. A starless world may, as explored already, carry a moon of its own, bound to it by nothing more than shared gravity, the two of them drifting together through a darkness that neither one alone would have to face. It may, if massive and fortunate enough, hold onto an atmosphere thick enough to trap whatever faint warmth its own interior still produces, sealing a genuine ocean beneath ice or gas that no star ever had to warm from outside. And, in at least one strange, remarkable case already described, it may not even be alone in the most literal sense available to a planet, bound not to a star, but to another world exactly like itself, the two of them locked together in their own private orbit, circling nothing but each other, out past the reach of every sun in the galaxy. There is something worth turning over in that image a little longer than the physics alone strictly requires. Two worlds, neither one able to offer the other any warmth or light in any conventional sense, both of them equally poor, equally dark, equally without a sun to their name, choosing, if choosing is even the right word for something gravity alone decided, to spend the whole of their existence circling one another rather than drifting alone. It is not a relationship built on abundance. Neither world has anything resembling a surplus of warmth to share. And yet the arrangement persists anyway, gravity finding a kind of company even between two worlds, with nothing obvious to offer each other, which may be as good a definition of company as any. In circumstances this stripped down. Alone, it turns out, was never quite the right word for the condition this entire hunt set out to describe. Unattached, perhaps. Starless, certainly, but not, in every sense that might matter, alone. A planet can lose its star and keep almost everything else that makes a world worth calling a world. Its heat, its geology, its water, in some fraction of cases, its very own moon, or its very own twin for company, drifting alongside it through exactly the same permanent dark. What such a world has actually lost, once all of that is accounted for, turns out to be a good deal narrower and more specific than the word darkness first suggested. It has lost a schedule. It has not necessarily lost everything a schedule was ever meant to make possible. There is a definitional thread from earlier in this hunt worth picking back up here as well, not to explain it again, but to see what it looks like once everything else has been laid alongside it. A planet. By the careful, technical definition astronomers settled on nearly 2 decades ago, must orbit a star to earn the name at all. It is a definition built, quite understandably, around the only kind of planet anyone had ever actually seen up close. Worlds discovered precisely because they circled a star bright enough to reveal them. But a definition built around the easiest case to observe is not necessarily a definition built around the most common case to exist. And everything gathered across this hunt suggests those two things may not be the same thing at all. If a genuinely large share of the galaxy's planet-sized worlds never orbited anything, then the very word planet, as currently defined, may describe not the ordinary member of its own category, but a favored, well-lit minority within a far larger, far darker family. The word was never quite built to include. Language, in cases like this, tends to lag well behind discovery, built by people working with whatever they could actually see, and only slowly, reluctantly, stretched to make room for what turns out to have been there all along, unseen simply because no one yet had the instrument capable of catching it. It has happened before, in fields far removed from astronomy. A word for a familiar, visible category is coined long before anyone realizes how much of the same underlying thing exists just outside what that word was ever built to cover, and only later, once the instruments finally catch up, does anyone notice the word was quietly describing a minority the entire time. It is worth sitting for a moment with just how recently any of this became something more than speculation. For the greater part of human history, going back long before anyone thought to wonder whether unattached worlds existed at all, the question would not even have made sense to ask. A planet, by definition, was a wandering point of light that circled the sun, visible precisely because it did. It took until the final years of the last century for theorists to seriously entertain the idea that planets might exist without any star to reveal them, and it took a further decade beyond that before the first genuine statistical evidence, however contested and revised in the years since, suggested such worlds might be common rather than rare. Even now, at the time this video was made, only a single one of them, out among the countless millions this hunt has spent so long discussing in the abstract, has ever had both its weight and its distance measured directly rather than inferred. That is not a small thing to sit with. An entire, potentially enormous category of planet, quite possibly the single most common kind of planet the galaxy has ever built, has been directly confirmed to exist as an individual, physically measured object only within the current year. Every other member of that vast, largely uncounted population remains exactly what it has always been. A shape implied by statistics, a shadow cast briefly across a distant star's light, never once seen for what it actually is. Measured against a galaxy some 13 billion years old, the gap between a population first suspected and a single member of it finally, individually confirmed, amounts to little more than the blink of an eye. A discovery so recent it has not yet finished settling into what people generally assume to be true about the night sky. There is one last shape worth noticing before this hunt closes, not in the worlds themselves this time, but in the hunt that went looking for them. It began with a number too large to picture, a population inferred from statistics alone, faceless and abstract, the kind of figure that slides through the mind without leaving much of an impression. It narrowed from there to a single, specific, individually measured world, a real mass, a real distance, a two-day flicker of borrowed light that turned an abstraction into something closer to a fact with a shape. It widened again briefly, to take in an entire nebula's worth of paired, twinned worlds that fit no simple story at all, complicating the tidy picture just as it seemed to be settling into place. It narrowed once more, down to the quiet physics of ice and hydrogen and buried heat, the small, patient mechanisms by which a single world, with no help from any star, might still manage to keep something warm and liquid sealed away inside it. And now, having met that one world, however briefly and however indirectly, having traced the strange twins that keep no company but each other, having sat with the physics of a hidden ocean no one has ever seen, this hunt widens back out one final time toward the full population it was drawn from, except the number no longer feels quite the same as it did at the very beginning. It is still too large to picture in any literal sense. No number this size ever stops being too large for that. But it is no longer entirely faceless, not after spending this much time with the one member of it that agreed, however unknowingly, to be found, and not after everything else gathered alongside that single confirmed world along the way. That is very often how a subject this size ends up feeling less abstract than it has any right to. Not by making the number smaller, which no amount of careful writing can ever do, but by making at least one small piece of it specific enough to hold on to, and letting that one piece stand, honestly and without exaggeration, for everything still too distant and too dark to see. That, in the end, is the plain fact this entire hunt has been quietly building toward, and it deserves to be left plain rather than dressed up into something grander than it actually is. Somewhere out past the comfortable, sunlit arrangement this planet has always known, in numbers no single survey will ever fully catalogue, there are worlds drifting that owe nothing to any star, worlds that may carry their own quiet warmth, their own hidden water, their own companions, sealed away behind a darkness that will never once be interrupted by a sunrise. They are not, on the evidence gathered here, a strange exception to how planets usually exist. Increasingly, that evidence suggests they may simply be how planets usually exist, and it is the bright, orbiting, sunlit kind, the kind every star chart and every childhood drawing has always assumed as the obvious default, that turns out to be the rarer, more fortunate arrangement. One star and one planet, faithfully keeping their old, patient appointment, circuit after circuit, for 4.5 billion years and counting, for reasons the universe was never obligated to provide. Nothing about this hunt has changed what Earth is, or what tomorrow's sunrise will look like, or how any of this ought to be lived with, day to day, by the people fortunate enough to live beneath it. What has changed, carefully, patiently, across everything traced here, is only the count, one more entry, however small, in the long, unfinished record of how the universe actually chooses to build its worlds, most of them, evidence increasingly suggests, without ever bothering to give them a sun at all. Look up tonight, if the sky happens to be clear where you are, and every star scattered across it is holding exactly that kind of appointment with something. But for every one of those small, faithful lights, astronomers now have real reason to believe there drifts another world nearby, honoring no such appointment at all, asking for nothing, expecting nothing, simply continuing, unlit and unhurried, through a darkness that was always, quietly, far more crowded and very possibly far less lonely than it looked. Even the worlds with no sun keep their own quiet warmth, rest now